Good morning. Welcome to the second day of this workshop. And as a first speaker, we have Alexander Razumov, who is going to present joint work with Yuri Stroganov, who is also here. And the title of his presentation is Three-Coloring Statistical Model with Domain Wall Boundary Conditions.
Well, thank you. I would like to thank the organizer for inviting us here and for giving us possibility to present a talk. Okay. I will talk about actually two models, very well known actually, I think, models. The first model is the three-color or three-coloring model, and the second one is the six-vertex model. I start with some definitions and with explanation and with reminding basic facts about these models. First, I will discuss three colorings. Then I will set about combinatorial problems related with this problem. And after that, I will discuss the relation of the three coloring model with six vertex model. The second part will be discussion of some functional equations which arise in the six-vertex model for a special value of the crossing parameter and for the domain wall boundary conditions. These functional relations, the proof of these functional equations is based on recursion relations which are satisfied by the partition function of the six-vertex model. So I will talk about them, and then I will talk about functional equation and give a sketch of the proof. Then the similar consideration will be applied to the three-coloring model with also with special boundary conditions. We call them also domain wall boundary condition. I think it will be clear why we do so. And here I will also discuss corresponding recursion relations, and then we'll show how using this relation one can prove the corresponding functional equation in this model. Actually, relation to combinatorial problems here arise first in six-vertex model. It's well known that the states of the six-vertex model is in one-to-one correspondence when certainly we use the domain wall boundary conditions, and in this case they are in one-to-one correspondence with the alternating sign matrices. So if we obtain some information about the partition function of the model, actually we have some information on enumerations of the alternating sign matrices. I will not discuss here this relation. I think the next talk will explain some basic points here. So let me start. So what is three colorings? in our sense, we consider a square grid or square lattice and try to color all the faces or cells of this grid by 3 colors, so that any pair of adjacent cells have different colors. So, for example, you have such a picture. Certainly, the color is not a mathematical object, and it's convenient to denote colors. In this case, it's convenient to denote them by the elements of the ring Z3. So we have something like this. And the condition that the colors of the adjacent faces are different is equivalent in this case to the statement that the colors of the adjacent faces differ by +1 or by -1, which in the ring Z3 is just +2. Certainly, the first combinatorial problem which arises here is to enumerate all 3 colorings and to obtain something, all possible ways to color. The second problem is to find some refined enumerations. Here I denote them by Cm depending on 3 integers. These integers means the number of faces colored in the corresponding color. It's convenient to introduce some generating function and treat the problem as a sort of a statistical model. In this case, we say that associate with each color corresponding number that which are treated as the Boltzmann weights of faces. If we consider some fixed configuration or state, we associate with it the weight, which is just the product of weights of the faces. And summing all these weights, we obtain the partition function or the state sum of the model. As it is common now, it's convenient to consider some parametric set of weights. So we introduce a spectral parameter. Okay. So we will introduce a spectral parameter and consider, you will try to find the weights such that they satisfy the star triangle relation. And in this case, we hope to have an integrable system and hope to find some exact results. Okay, I will interrupt discussion of 3 coloring model and consider the connection with the 6 vertex model. This relation was first considered in 1961 and can be described as follows. I remind that the states of the 6 vertex model are defined in the following way. We consider again square lattice, and choose direction for each edge in such way that the ice condition is satisfied. This condition states that at every vertex there are two arrows pointing in and two arrows pointing out. For example, in such a way, and a possible state is given here. So let's return to the three coloring model, and it is not difficult to understand that we have here three possible, six possible different configurations. Each configuration is parameterized by color, denote here by mu. And actually you have 6 by 3, 18 configurations. And let us consider a vertex and consider 4 faces which contains this vertex. And let us start with any face and walk anti-clockwise around the face. And if we intersect an edge and see that the color changes by +1, we draw an incoming arrow. And if we see that, for example, here, oh, not here, here, the color changes by -1, we draw outcoming arrow. It's not difficult to understand that the ice condition will be satisfied here, because we, after we made a full circle, we have to obtain the same color. And it is not also difficult to understand that there is no contradiction in this definition, which can be connected with the fact that we can each face contains 4 vertices, and we can go around each of them and probably obtain different results, but it is not difficult to understand that there is no contradiction here. Okay. Actually, it is more convenient to consider our model as a partial case of the so-called interaction around a face model. In this case, the weight of a state is defined not as a product over faces, but as a product over vertices. And if we associate with each with a vertex the following weight, you see that we obtain the same partition function, because it's true for toroidal boundary conditions. Each face enters 4 vertex configuration. So when we multiply all the weights, we obtain right weight, the right weight. Okay. Using this formulation, Baxter found the corresponding partition function of the model in the thermodynamic limit. For a combinatorial problem, it's certainly important to have information about finite size lattices. So it's not interesting, this result, from the point of combinatorics. And we will try to move further for finite size lattices. So, as I said, we will try to define weights for vertices using spectral parameter u. Here you can see notation for the corresponding weights. Okay, and the first time the solution of the star triangle relation was found by Stroganov in his unfortunately unpublished thesis. And the weights here are expressed via theta functions, and the solution contain an arbitrary parameter alpha. An arbitrary parameter alpha. Oh, you see, it enters. If we put the spectral parameter equal to pi over 3, it's not difficult to see that the weights take a very simple form, and actually we come to 3-coloring model considered by Baxter with the weights connected with the function zeta in this way. And actually changing alpha and norm of the elliptic function p, we can change that mu and actually have the same partition function. Okay, and now I will remind that for the 6-vertex model there is very convenient representation for the partition function via Isергin-Karepin determinant. Actually, in the case of the domain wall boundary conditions, the partition function is known. If we calculate the corresponding determinant, we will obtain the partition function. And okay, the weights of the 6-vertex model in usual parameterization have the following form. The weights also depend on some arbitrary parameter eta, which is called the crossing parameter. And it is known, now it's very well known, that for eta equal to 2 pi over 3, and for the domain wall boundary conditions, I will explain what these conditions mean. The partition function satisfies some simple functional equation. And in this case, one can solve this equation and obtain another representation for the partition function. And this representation is very convenient for the, I said about this, for solving enumeration problems for the alternating sign matrices. I would like to show that the partition function of the 3-coloring model for appropriate boundary conditions also satisfies similar equations. Similar equations, actually, not one equation. The proof of the functional equations for the case of the 6-vertex model is based on I said about this, on the recursion relations discovered by Karepin. And as I said, these relations can be used to discover determinant representation of the partition function. And using this representation, one can prove the functional equation I said about. And we can try to use the same sequence of steps for the three coloring model. Unfortunately, we have a recursion relation for this case, but we have no determinant representation of the partition function. And it appears that functional equation can be proved directly from the recursion relations without determinant representation. And I will discuss this, and we will use this fact that there is a direct way to prove functional equation for the three coloring model. Okay. The six-vertex model with domain boundary condition is described as okay. Consider a square lattice and assume that the on the on the boundaries the rows are pointed here we have only incoming arrows, here also, and on bottom at the top we have only outcoming arrows, and if we say it with some spin these arrows, you have something like domain wall. And here it's convenient to consider in homogeneous model. Here the spectral parameter associated with a vertex is difference of the spectral parameters associated with rows and columns. So here we have x1 minus y4 and so on. Let us consider the bottom rightmost vertex in our situation. And it's clear the direction of two arrows is already fixed. And we have two possibilities for remaining two arrows. The first possibility is this one, and it corresponds to this vertex with this weight. Here n is the last index here is 4. And the second possibility is this one. And the weight of this vertex is just 1. If we put this argument to 0, then the configuration with the first choice of rows give no contribution to the partition function, and we have only a contribution corresponding to this choice, and we assume that xn is a dependent variable, and it is yn minus eta 2. Okay. If we made this choice, it is not difficult to see that the directions of these and these rows are fixed. There is no freedom, and we have possibility to choose direction of arrows only here. You see that we have again here domain wall boundary condition, and we can just write explicitly the weights corresponding to these vertices, and they will be multiplied by the partition function for the lattice of size n minus 1 actually.
So there are 3 incoming.
Yes, this is.
Where is it? 3? Ah, sorry.
On the whole right column, there are 3 incoming arrows, 1 up. Which probably means that
Yes, the horizontal one shifted in order to make boundary conditions.
But
So three of them are
should be opposite.
yeah, I believe that is so.
Верхний правый там стрелка.
А где?
Right top.
А, вот это, да? Окей. That's right. Okay, in any case, we have this recursion relation. So the partition function Zn with one argument fixed is expressed via the partition function Z for n minus 1. Okay. Actually, the partition function Zn is symmetric in separately in the variables x, y, and yi. It can be proved using the star triangle relation. This trick is very well known, and I will not explain it here. Nevertheless, it is true. And actually, we have n squared recursion relations. K is from 1 to n, and L is also from 1 to n. Actually, we can start not with this vertex, but for example from this one. And in this case, we obtain a different set of recursion relations. The difference is that here we have minus sign here, and here we have plus sign here. Plus sign here. So we have two n squared recursion relations, and knowing the partition function for n is 1, we can construct actually the partition function for arbitrary n. Okay. So how to come to the functional equations? Here it's convenient to multiply the partition function by such factors, and after this one can wonder what recursion relation are for function fn. Okay, assuming now that eta is 2 pi over 3, the special value of the crossing parameter, we see that the recursion relation take this form, and it's important to see that here we have 3. So if we shift any argument here by, for example, 2 pi over 3 or 4 pi over 3, this factor does not change, but we simply shift the corresponding argument here. Now let us define such sum. So we take our function fn, then shift argument, without shifting argument, then shift by 2 pi over 3, and then by 4 pi over 3 again, and sum the results. And it is not difficult to prove by induction that this sum is 0, just 0, identically. So actually, it's clear again from the symmetry of the partition function in the variables x, y, that it's sufficient to prove that it is this relation is true for n for k is 1. And the base case of induction is the case when n is 1. Okay, in this case we have this simple identity. Everybody can verify. So now we assume that this sum is 0 for some n. For some n, the recursion relation gives us then that this function, let us consider this sum as a function on xn, the sum of xn. And you see that from the recursion relation follows that for xn equal to yl plus minus pi over 3, it is 0 again. So we have 2n zeros for Sn. Now let us count zeros, all zeros and orders of our functions. It's not difficult to see that with respect to the variable xn, not only with respect to xn, with respect to each x, the partition function is a trigonometric polynomial of order less or equal to n minus 1. Actually, it's equal to minus 1, but it's enough for us. It's almost evident that it is of order less or equal to minus 1. And you remember that Sn is obtained from Fn, and Fn is obtained from Zn by multiplying by some product of signs. So the order of Sn, it can be calculated, is less or equal to 3n minus 2. And as a trigonometric polynomial, it has at most 6n minus 4 zeros in the interval from 0 to pi. Okay, so let's count zeros. Recursion relation give 2n zeros. By construction, by multiplying by signs, you can see that there are 2n minus 2 additional zeros at the points. Oh, sorry. Okay, and again, one can show easily that the sum, actually the partition function and the function f and s satisfy this parity relation. Sorry. Oh, sorry. No pi here, certainly. So this relation doubles all zeros in general position, certainly. And you see that S has 8n minus 4, should have 8n minus 4 zeros in the interval from 0 to pi. And it is possible only in the case when S is identically 0. So we prove the following functional relations for the function f, or certainly for the partition function, because f related to partition function in a direct way. Okay, so let us try to go this way for the three coloring model. First, we will try to define what we mean by domain wall boundary conditions in this case. Okay, first, I would like to say that it's natural to represent the partition function in this case as the sum of three partition functions, partial partition functions, labeled by mu, where mu is, for example, is the core color of the left topmost vertex of the lattice. Actually, you can fix the color of any boundary face. Not vertex, face, yes, face. There is certainly correspondence, yes. Okay, for example, we fix here this color, for example, by 2. And now I will explain what we mean by domain wall boundary condition. If you start, in this case, from any face and walk anti-clockwise, and the color change by +1 for vertical boundaries, see, +1, +1, +1, +1, and by -1 for the horizontal boundaries. -1 is 2, -1 is 1, and so on. So if we consider the corresponding state of the 6-vertex model, you will see that it satisfies the domain wall boundary condition for the 6-vertex model. Here we have incoming arrow, if you remember, and here we have outcoming arrows. Okay, again, we consider in homogeneous case, so we associate first spectral parameters with horizontal and vertical lines, and associate with a vertex again, spectral parameter which is difference of these parameters. Okay. It is convenient to actually use slightly changed weights for vertices, which can be obtained using gauge transformation of the vertices. What is here the gauge transformation? If we use this notation for weights, so and consider instead of weights W, W with tilde, which are given by this equality, where the function phi satisfy this simple relation, so some exponent it's actually on U. And if we choose this function as phi, then we come to the following weights. More simple actually. Why we did so? Actually, we lose here direct relation to the 3-coloring model, but because we used a gauge transformation, the new weights also satisfy the star triangle relations. And for example, for the toroidal boundary conditions, we have the same partition function, we obtain the same partition function using these new weights. In our case, for the domain wall boundary condition, there is some fixed contribution to the partition function from the boundary. Actually, it's connected with the fact that now not each face belongs to 4 vertices. Boundary faces belong to only sometimes to 1 or sometimes to 2 vertices. But the reason to use these weights is that for these weights, the partition function, new partition function, functions are symmetric in the variables x, y, and xi and yi. And this property was actually very useful because it allows having one recursion relation obtain n recursion relations, n squared. Okay, now recursion relation, the same procedure. We consider some fixed phase and see that there are 2 possibilities to color this phase. The first possibility is to color it in the color 1 with this weight, and the second possibility is to color it in color 2 with this weight. And again, if we assume that this argument is zero, then only the second class of configuration contribute to the partition function. So we assume that xn is yn plus 2 pi over 3. And again, in this case, the colors here become fixed. Nowhere here. Okay, it's okay here. So again, we come to the configuration with domain wall boundary condition, can verify, and again come to the recursion relations, starting with the top rightmost vertex. We come to the second set of recursion relations. Actually, it's important here that first of all, here we have a factor which depend on weight, on the color. Here, overlying mu is just integer corresponding to the element of the ring Z3. And it's important here also that here we have actually the same partition function, but here we have shifted index, the partition function for shifted color, shifted by 1. So if we just take a sum of the, multiplied by some factors of the partition function corresponding to the one color, we will not come to desired results because color will change.
Excuse me, may I ask you, is it true that what you have shown us combinatorially on the graph is the first equation and the analogous one with epsilon n minus 2 pi over 3? I don't see the second one. Is also a consequence of our discussion, or is
Yes. These relations follows if we consider the bottom rightmost vertex, and we obtain this first one. And the second, if we start with the top rightmost, the same consideration can be applied. If we consider this, and here we have also two possibilities to color, and again corresponding weights, and we choose parameters so that to choose only one, and so on, the same procedure. In this case,
I would have guessed that in this case one gets xn equal 1 yn minus 2 by 3, but instead it's just xn equal 1.
Yes, the different. It's.
Before it was really symmetric, just plus minus.
Yes.
1, and here it's different.
I see. Yeah. Okay. Here it's different. Yeah. And yes, that's right. And here you see that the second one is shifted color. Can be explained very well. So if we start with this, and the configuration remaining will be here, and here we have not color 2 but color 0 in this case. So that Z corresponding to the shifted color. And when we start here, the color here remains the same. Okay. So again, we introduce the functions f. Here we introduce this factor. So to get rid of this factor actually, now if we use this relation, it can be proved very simply using usual properties of theta functions. So, and we have the following recursion relation for the function f. Here again, we have 3. And to use this property to define first the sums, our sums. And you see here that we not only shift the argument, but also change color here. So again, using recursion relation, we see that these sums has 2 and zeros and the corresponding points. And again, by construction, multiplying by some thetas, we have additional zeros at these points. Again, the relation, okay, I can notify here. So, this relation doubles all zeros, and so the function has 8n minus 4 zeros in the interval. Now one can count the order of the function Sn. It is now probably not the order. It can be shown that if we consider this sum, and try to find periodicity factors for elliptic function, we will see that each term of this sum has the same periodicity factor. So if we divide all this sum, for example, by its first term, we obtain a doubly periodic function. And we can calculate the order of this doubly periodic function. And you know that the order is the number of zeros of the doubly periodic function in the corresponding cell, periodicity cell. And so we can see that it is impossible for this function to have so many zeros, so many zeros in this interval. So it's possible to have this of zeros only if this function is identically zero. So in this case, we again come to functional equations, but having a very similar form. And the only difference here that, again, I repeat that we not only shift an argument, but also shift color for the corresponding, actually, partition function. So we have functional equation. Unfortunately, we have not succeeded yet in solving this, but we hope that it can be done. And if we will succeed in this, I think it will be possible to solve some enumeration or combinatorial problems. So I think at this point I will finish. Okay.
Very much. Are there any questions?
So, do I understand correctly that you don't have a guess for any determinant formula, or is it a stronger statement that you know there is no determinant formula?
I think there is the determinant formula, but we have not yet found
one
it.
Determinant?
Actually, this formula is not convenient. No, it can be used for combinatorial problems, but when you use, for example, for 6-vertex model, determinant representation, and try to associate it with some enumeration, you have to fix parameters. But determinant is singular at this point, and so you have to use some limiting procedure. If you use the solution of a functional equation, there are no such problem. you have a direct way to connect, no, to find enumerations. Just refine it and so on. So I don't think that it is very it will be very convenient for our problems to have determinant representation.
So you need
Well,
some
no, it-
explicit expression of some kind.
Yeah.
Like integral or something.
Yeah.
The six-part case is the function is the symmetric in the whole set of variables and variables.
We have no this property here. You can just consider no, for some small n using a computer and see that there is no symmetry in all variables here.
Questions?
Maybe a comment that there is some analog of the is there incorrect in determinant, that it's not just one determinant but a sum of determinants. It's some
Analog for which situation?
but in this elliptic situation. It's
possible that this one of these functions, really three different functions, can be presented as sum of three determinants,
yeah.
which are similar to determinant. It's possible, but we don't yet.
Well, I think. Can you speak louder? I think it's in a recent paper of mine. It was in the archive maybe 2 months ago. So we can talk about it.
Okay, so we have no,
So he said
no
that he thinks that
determinant
there is a
representation.
solution in terms of the sum of three determinants in a recent paper of his. He will talk. He will talk to you after.
Okay, okay.
So, more questions? Solutions?
Thank you.
Okay, if this is not the case, then thank you again very much.